Welcome everyone to the next Lunchtime seminar in our series. Today we are hosting Iftikhar Ali, who is our PhD researcher here in CFPR. And Ali started in 2022, and his research topic is 2D materials-based energy harvesting textiles. Today he will share with us some exciting findings from his project, which was also published in EcoMat Wiley. And hand over to Ali.
Thank you. Hello, everyone. So, as Julia said, today I am presenting some of my initial result, which is published in EcoMat YD. The impact factor is 14.6 something. So the title of the article is Textile-Based Triboelectric Nanogenerator, which is integrated with 2D material. So here is the working mechanism, or you can say system design. The cycle just is a motivation that this project was initiated for cyclists. And what is presenting in this figure is why not you have these all things, like you are harvesting your motion and converting it to electricity, and then you have also capability to store those energy, and in real time you can use it as a self-powered indicator light. You can power your LED lights. As you know that in UK in winter there is quite dark, and the figure B is showing the mechanism of the device. So in the central figure, this show the configuration of the device. So what we have is cotton fabric, which is sandwich using a sponge as a spacer. First of all, I would like to give you a brief idea about triboelectrification or triboelectric nanogenerator. So triboelectric nanogenerator is work on based of triboelectrification. Triboelectrification is a mechanism where two dissimilar objects come closer in contact, so they share some charges, and those charges are then separated using electrode in external circuit like load. So there are two basic mechanisms. One is triboelectrification, which is contact when two dissimilar objects come closer in contact, and one is electrostatic induction. So what is electrostatic induction? When there are two different charges, like when you bring one charge to another surface, it charge the opposite surface. Maybe you remember in childhood when you comb your hair and then you come closer to some paper particles, it was attracting those things because the opposite charges are generated on the those particles. So this is actually that mechanism, but in more scientific way, we are accumulating those charges through external load and resistance. So what happened when you press the nanogenerator initially? So it is a triboelectric effect where you get a peak. You can see in figure C, you get a high peak, which is voltage, and then while you are well, it was releasing, then due to the electric field, because of the electrostatic induction, a negative peak also occurs. So this is like a cyclic positive negative peak with pressing and releasing, and those energies harvested in this way in triboelectric nanogenerator. Here is a mechanism of how we fabricate this device and develop this device. So in this complete project, only screen printing and drop casting is utilized. So initially what we have done, like printing conductive electrode using graphene material, and using a screen printing, we printed graphene as electrode. Then on graphene, we printed insulator paste, which is working as a triboelectric layer, like having this different electron affinity, or you can say dielectric constant. And another way, we started to enhance the result while using another 2D material, which is molybdenum disulfide, and we drop casted over graphene. And then for the another triboelectric layer, we use Kapton tape as another triboelectric layer, and then combining these two layers, We use sponge as a spacer using double-sided adhesive tape. We pick sponge on the edges of these electrodes and then pick the other surface on it to make a sandwich structure, which is triboelectric nanogenerator. So this is the fabrication and development of the device, which is quite easy and straightforward method. So here we come to the result discussions. The purpose was to how the 2D material will influence the performance of the device. So for this, I built 6 devices, which is like varying the concentration of molybdenum disulfide in just one single layer. You can see the PVA plus MOS2 layer in figure A. So in this layer, we made variations to see what happened while increasing the concentration of the molybdenum disulfide, which is 2D material. So we made 6 devices with only graphene. There is no like without this layer, molybdenum disulfide and PVA, and with only PVA, and then increasing the ratio of the molybdenum disulfides like from 0.1 to 2 gram per liter. So you can see here there are some points which I want to say you like the PVA gel. Many researchers have reported the same behavior, which is not very clear yet. But the thing is, when you leave it to dry in ambient environment, it takes up to 3 weeks to give you high peak output. And while you dry it in thermal condition, like curing with furnace or something, then a plastic layer is created on the layer, and the result is not that much good as in ambient environment. So we got good result after third week. You can see with only graphene, the open circuit voltage is around 580, and here in while including only PVA, like not MOS2, the results is far better than only graphene, and we go beyond 600. But as we started with molybdenum disulfide, the results increased, and we got the optimum result with 0.5 gram per liter concentration. And there are many reasons, but some of the reasons it's like initially, uh, like when you are including molybdenum disulfide, it was helping to accumulate charges, but while high concentration, it was leaving aggregation on the surface of the graphene layer, and it was like the kept on tape was not capable to fix as with low concentration due to the aggregation of the MOS2 layer. So we got the optimum results. This was optimization with 2D material. So we got the optimum result with 0.5 gram per liter of MOS2. Then we go further with the structure optimization. So what happened? I got like, okay, 0.5 gram per liter. Let's try with double side. Initially, we were trying to use with single side. Here, I tried to use the double side. So with double side, we got less result as compared to the single result. And the reason is, as I already told you in the start, that for triboelectrification, you need to have dissimilar surfaces. So while using similar things in the same side, the result was reduced as compared to the single side one. Then to further optimize, I increased the passes of the insulator paste. That what happened if we increase the thickness of the triboelectric layer. Kapton tape is fixed one, we cannot change it, but the insulator paste, which is screen printable material, so I use 3 passes from starting from single pass, then second pass and third pass. So you can see it, the first pass was 570 micrometer, and we got good result with 570 micrometer. These are the limitation of the screen printing, so we were not went below this thickness. But the reason behind this is as much as the layer is thinner, the triboelectric, it is easy to accumulate charges. It is easy for the electrode to accumulate charges from the tribo layer, and that's why the result was better with thinner one. Then another structural optimization, like what happened if we increase the thickness of the spacer, which is sponge in our case. So I started from 1 mm to 12 mm, and we got the optimum one with 0.5, 5.5 millimeter of thickness of the sponge. And the reason is, like, initially it was helping to increase the electric field between these two layers, and it was helping to get more high peak. But as we went beyond those like 5.5 millimeter thickness, then it was hard to maintain the electric field for the layer, and that's why the result got decreased rather than increasing further. And then I tried to see what happened if we increase or decrease the area. So what is the response? Is it linear or not? So you can see in figure D that while using 1 by 1 cm square device, then 2 by 2, then 3 by 3, the result was increasing. But like after 4 by 4, it was hard to maintain both the layer, and using the sponge with 5.5 meter, it come closer because of the tension of the fabric, and we got the better result with 4 by 4 centimeter square. Figure E shows that how it either we get any decay, like the endurance cycles, either we get any decay with uh, checking it with the durability of the device. So I run it continuously up to 1,000 cycles, and as you can see that there is negligible changes in the output. Uh, you can see in figure E that there is no changes, and it was giving continuous similar peak and similar results. And similarly, the figure F shows the fatigue test. We call it bending cycles, but my examiner suggested to use fatigue test. So it is fatigue test to show the flexibility of the device. So I used to bending it up to with around 8 mm rod, like per 100 of cycles, and only 4% reduction was occurred after 100 cycles. So it shows high flexibility of the device. So then, after getting like structural optimization and 2D material optimization, then I tried to characterize the find the electrical performance of the optimized structure. So building a device with 0.5 gram per liter concentration of MOS2, single side, and 5.5 m spacer, and those optimized value. And then I check like what happened if we increase the force or stress. So it was the machine limitation that we went up to 22 Newton force, but with 22 Newton force, we got around 1068 volt, like 1000 plus volt. The current was low, but the voltage was quite high, like more than 1000 volt. And similarly, to see the frequency. So initially, there was some changes, like from frequency 1 hertz to 8 hertz. There was 1.2 times, 1.2% increase, but there was not that much difference with frequency. It was giving similar result. So then I measure the power density and current and rectified voltage. Why do we rectification? Because there are negative peaks, so we want to see the one side of the to rectify the negative peak and get it positive as well. And we got around 14.4, 14.64 watt per meter square power density, which is higher and like 3 times better than already published work. Here is the comparison table, you can see it. So, okay, now energy is generated, but what if we store this energy as well? So this is the storage, energy storage unit. So I built and fabricated textile base supercapacitor. And these are the electrochemical characterization of textile-based supercapacitor. So we got 4.9 millifarad per centimeter square of capacitance. And similarly, these all are showing the electrochemical characterization like the cyclic voltammetry, GCD curve, and then looking at what happened if we bend it, or showing the flexibility. You can see the figure D, there was negligible changes while bending with different radius or diameter. And similarly, you can see figure E, it was showing like if we find the GCD curve of single device and then connecting three devices in series. So you can see that with similar time, uh, single device can reach up to 1 volt, while connecting three devices in series reach up to 3 volt, which is showing that the consistency of the fabrication of these devices. And then the endurance cycles like charging discharging curve up to 5,000 cycles. So it was like around 3.5 or 3.7% reduction in results. So now coming to combine these results with the nano generator and the capacitor together. So these are the application. Figure A shows the schematic illustration of how we are connecting silver capacitor with nano generator. So there are rectifier circuit, as I told you, that we also want to utilize the negative peak. So we use the rectifier circuit to make the negative peak positive as well. And the figure B shows the practical photo of the experiment. And figure C shows like, in less than 300 seconds, it get charged up to uh, 10 volt while connecting 9 supercapacitor in series. Why we are connecting in series? To get high voltage rating. So then figure D shows like some commercial capacitors that as we increasing the capacitance, it takes more time to charge. And figure E shows these all are like, I will show you some real-time videos corresponding to each of the figure. So let's move to the clip one. So it is charging 9 supercapacitors with just tapping. It is 4 to 5 Newton force, and you can see on the DMM that it is getting charged. So this is the real-time application, how we generate and store energy in our self-powered system. You can see these are showing the commercial 4.7 microfarad capacitor. You can see on the screen of DMM, it is getting charged to 1 volt in just few seconds. So these are like, not only you can generate electricity, but you can also use this device as a self-powered step counter, or for many other sensing applications. Like you can use it as a button, you can use it as a switch, you can use it to play music, you can use for various applications in IoT. You can see in this video, it can power more than 160 LEDs, and in dark you can see more glowing it with more. You can see CFPR UV. Then this video shows like, well, I fixed the device in SOC, and you can see that it is working in real time while you're running, while you're walking. It generates electricity, and you can glow your indicator light or things. So that's all. Thank you.